Which is
Thank you, George. Actually, you heard the answer, about 4 weeks ago, when the speaker said the reason for learning assembly language is that the bottom line here is no matter what you're programming in, you're controlling hardware. So I'm going to dig down into that a bit today. And I'm going to first address the question, why use a computer in the first place? Speed is probably the first thing that pops into your mind. And it's not just that we have impatient users. We'll talk about this. Another thing is that you make many fewer errors, like data entry errors and all of that. As you're copying things by hand, you tend to make errors using pencil and paper. It's a lot easier. Also, it's easier to change. Once you commit something to hardware, it's really difficult to change it. And it's just a lot easier to change software. So those are some of the reasons for using a computer. Okay, I'm going to do this within the context of how I got into it all. And I got my bachelor's degree in 1962, a long time ago. In case you don't have a calculator with you, I'm 76 now. So it was a long time ago. And we were in the middle of a space race. We were trying to put a man on the moon. And yes, women, in those days, only men got to be astronauts. The world's changed a lot since then. And so within this, I'm going to talk about the speed and accuracy of computation. And what I worked on, I worked for a small company down in Mountain View that built the horizon scanner for this, for the Gemini capsule. And the way it worked was there was a little mirror on a little tiny meter movement or motor that locked onto the Earth's horizon. And one of the jobs that I had to deal with was keeping this thing locked on with a feedback control loop. And this was an all analog design. And what I had to design was a compensation circuit for the feedback control loop that consisted of resistors and capacitors. Okay? Now, solving those equations involves solving a system of several simultaneous linear differential equations. Now, in principle, you can do that all with a slide rule. In fact, the very first one that we built was done, my boss actually designed this circuit using a slide rule, and he used a lot of approximations because this is a very time-consuming process and fraught with many, many errors. If anybody's ever, probably none of you have tried to do this with pencil and paper, but it's hours. And I can't remember how many equations we had here, but it was in the order of 5 or 6 differential equations that we had to solve. And not only that, there's no way to sit down and do this. Here's the input I want and the input I have and the output I want, and just solve it. It's a trial and error thing. Okay? So the first one that we built worked like a champ. And in fact, we were the only major subcontractor. What are they doing out there? Are we in danger? Well, this morning when I live up on the hill and it was foggy up there, and somebody landed a hot air balloon here. So who knows what's going on?
I just learned CPR.
I see. Okay. So there's another class going on. Okay. So the first one we designed worked quite well. In fact, we were the only major subcontractor who delivered on time, McDonnell Douglas. And so that worked quite well. Unfortunately, when we put together the second one, it didn't work. And it turns out that we were just lucky in all capacitors and resistors have tolerances, and we were just lucky that we got the right combination. And what this meant was that we had to actually sit down and solve the real equation. We had to be more accurate. And so I wrote a Fortran program. Okay, so this is the speed and accuracy of computation using the computer. Okay, fast forward about 15 years, I went back to graduate school, and actually my specialty was bioengineering, and so a natural job for me was working for a company down in Cupertino. Cupertino was a lot different then. This was before pre-Apple computer. This was in the late 70s. And I was hired by a company to work on a CT scanner design. So this involved real-time data collection. And what we had to do was collect X-ray data, and of course the patient can't move while you're collecting the data, and I'll show you here how it works. What it does is it uses what's called back projection to reconstruct an image. And to give you an idea of how this works, imagine that I have an X-ray source here and a detector over here. Now then, there's something in the way, and what you can see here is that this line here is sort of gray because there was something in the way here when there's this X-ray shine through, and it's opaque to the X-ray. Okay, so I rotate the thing a little bit, and I get another projection here. Okay, now you're starting to see where this thing is. And a third one here, you can see where this thing is. And so I have a slice through the brain now, and I know that there's something there. And most of you can probably see that there are a lot of artifacts there. I was in charge of making the scanner go and collecting the data, and then another guy, also named Bob, was in charge of the algorithms that took care of this. But the point here is that this thing had to go really, really fast because the patient can't move. Okay? So what we're talking about here are embedded systems. And an embedded system is where the computer is dedicated to a specific functionality. Okay? The distinction between an embedded computer and a general purpose computer is gray, but you can kind of get an idea here if you compare a flip phone with your smartphone. The flip phone is an embedded system. The computer there is just doing telephone stuff. You add functionality to a smartphone, and now you're adding in general purpose computing. So you can add apps and all of that. Now, I talked about things so far, about things that were going on decades ago. You guys are going to be working with Internet of Things, robotics, smart vehicles, wearables, things like that. And these are all embedded systems. Usually it involves highly specialized hardware, and you have to know how that hardware works in order to program it, of course. And often there are real-time constraints. I mean, I showed the CT scanner, but you start thinking about some of these other things here, smart vehicles, and now, real time is real time. Often, we're with these devices too, we're very concerned about efficiency, not only speed and memory size, but power. They're typically battery-operated devices. You want them to run for a long time. Okay, so to make sure we're on the same page here, I'm going to give an overview of computer hardware. Probably most of you, if you've used my book, you've seen this. In fact, it's figure 1.1. And it includes
CPU, the central processing unit. One of the keys here is that it's clock-based timing. So everything happens according to a clock running. There's the memory. The memory now is time synchronized to the CPU. And it involves random access memory. Actually, the terminology is weird. It's read-write memory and then read-only memory. There's a historical reason for random access. And then we have input and output. And if you're working with embedded devices, this is the kind of stuff, this is the area you're going to be concerned with. And the issue here is it's not synchronized to the CPU. Typically, these are things that transform the bits into some kind of human usable format. It can include mass storage, like a disk, the cloud, things like that. Those are all dealt with in input-output. Okay, digging down into the CPU a little bit, we have these boxes in here. And here's the interface to the address and to the memory and the I/O stuff. Okay. Now, I said at the beginning that the reason for studying assembly language is because, bottom line, you're dealing with the hardware. You have to make the hardware do things. The way you make the hardware do things is you put a bit pattern in the instruction register, and that causes things to happen in here. And I've programmed that way before. Trust me, you don't want to do it. Well, some of you may. I don't know. It is kind of fun, actually. But anyway, there's a one-to-one correspondence, as most of you know, between the assembly language instruction and this bit pattern here. And so this bit pattern, if we put it in the instruction register, will cause the value in register R12, the 64-bit value, to be added to the one in register R15. Okay? So again, the assembly language is a one-to-one correspondence between the machine language, which is the pure bit pattern. People often are a little sloppy and they talk about assembly language. They call it machine language, and that's okay because it's a one-to-one correspondence here. Okay, I said that it's easy to make changes. That's one of the reasons we use computers. And high-level languages are certainly easier to read. And so if you want to make it easy to change, then you really should use a high-level language whenever possible. And you should use appropriate variable names. For example, that previous instruction in assembly language is gobbledygook to most people. But if here you say, oh, I'm adding somebody's pay to the balance, so I'm increasing the balance. So if you use reasonable names, it's a lot easier to read and therefore a lot easier to make changes. But compilers can differ. Now this, I don't recall, this is from some 25 years ago, and I don't recall all the details here, but some students stopped me in the hall one evening, and they were working on this problem that an instructor had given them. And the question is, what did this print out here? And it was late at night, and I said, well, try it. And then I went home, and I had access to 3 different C compilers, and I got 3 different results, depending upon how the compiler writer interpreted what the rules were for that compiler. Okay, now it's getting better in today's world, but you just have to be careful. You have to be aware that compilers may not do what you think they're doing. And so the bottom line here is that you need to program the machine, not the language. So you have to understand what's going on with the machine here. Some hints here is please avoid showing off your knowledge of the language. It's cute, but it's hard to change. I'll do an aside here. I'll guarantee that the first job you'll get, you'll be changing somebody else's code. I will guarantee that. Okay? So I had a PhD when I got my first programming job. And my first job was to port. In fact, I told you the CT scanner, they'd already built that. I had to port it from one computer to another. I had to modify somebody else's code. Another hint is to break things down into simple, easy to follow short steps. Another thing to remember here is each higher level language has its own grammar rules. Does a logic expression evaluate right to left or left to right? The hint here, by the way, is use parentheses everywhere. That'll help you. Another thing to know is that when you do write a long expression, there are a lot of hidden variables that get created for intermediate values. Okay. Here's a program for you. It's in C, but I think most of you can probably read it. You've had enough higher level languages. The main program here calls this function, and then it calls this function. The first function creates an array, 100 elements, and it fills it up, the numbers 0 through 99. The second one creates an array and prints out those numbers. What does it print? It's 0 through 99, right? Is everybody happy with that? I mean, I go for I running from 0 up to 100. I put the integer in there, and then here, you may not have had the printf statement yet, but it just prints out the digital value, or the decimal value of what's in that array element. So it prints 0 through 99. So that's what the program does. Is this program correct? Anybody hazard a guess?
I mean, it'll print it, but you didn't make it persist through the function. You're just reading it off the stack, right?
Exactly. So this program, in fact, seems to work correctly because it turns out that this function creates an array on the stack. When it returns, that is technically garbage, but since I call this other function right away, the values are still there, and it just happens to print them out. And so it's surely accident, and so it's the program is not correct. Okay? Now, and what happens, I'll guarantee, is down the road, a couple of years from now, if the code's any good, somebody's going to come along and put another function in here, and it trashes the program, and nobody can figure out what's wrong. Another thing to know is that making it look simpler in a high-level language does not mean it's really going to be any simpler at the machine level. I think the F1 function up there looks a lot simpler than this. I mean, good grief, I've created all these, these other variables, and I do this and that, and they do exactly the same thing, but that one up there is certainly a lot easier. But let's look at what the compiler does with them. This is F1, and this is F2. Exactly the same thing. So the compiler, even though I've written this nice, neat expression, has to create these intermediate values. And so it does exactly the same thing. So even though it looks simpler in the single expression, at the machine level, it's not. Now, one of the things I've learned in my years of programming, by the way, for those of you who don't know, I was a programmer, I was a software engineer out in industry for over a decade before I came here and taught. So I do have, quote, real world experience. And I've had to debug a lot of stuff. Trust me. when you separate things out, remember I said do everything in short, simple steps. When you separate it all out, it's a lot easier to debug this code than that long expression, because you can set a breakpoint here and you can look at that value and you can see if it has overflowed or something like that. This one is a hell of a lot easier to debug. Okay? Okay, now I'm going to talk about some CPU features. This is just a repeat. One of the things that the Intel chips have in them is the capability of doing some parallel processing here. So the MMX registers are 128-bit registers, and this instruction, PADD, parallel packed add, will simultaneously, if I have 32-bit integers in a couple of registers, add them together and store them in a third large register. Now, I had the opportunity to, some years ago, work with it was before Apple changed the Intel chips. They were using the Motorola chips, PowerPC, and it had a similar kind of thing. And one of the pluses that they advertised was that you could program it in C. All of the C functions that you had to call to do it were basically the same as the assembly language instructions. The bottom line is, if you're going to do any of this stuff, you have to understand what's going on at the assembly language level. There is no high-level language that's just going to do this for you automatically. And it's, doing parallel processing like that. We were doing a fast Fourier transform, so it was a math-intensive application, and I picked up a factor of 2 or 3 by doing that. Now I'm going to talk about programming I/O devices. As I said, they're not synchronized with the CPU. So you have to write let me go back here. You have to write the code to talk to the machines out there, or the devices. Okay, so let me give you an example here. This function here will read, let me preface this with, this is kind of, well, it's a great simplification. It's taken from a class that was taught here a couple of decades ago, and it was a very simple processor that we were using. And I've simplified things quite a bit here to illustrate the point. Okay, what this does is it reads a single character from a device that is a character device. And what it has to do here is the first thing it has to do is read the status register. Okay? And there's a single bit in that status register that when it goes to 0, then that means the device has a character ready, and so I can read the character. So I read the character. So it's sitting here in this do-while loop until, and these are constants that I have pound defined. So I define them. This is simply a bit pattern here. And so it's doing a logical AND here with the status word, when I read the status word, and it waits until it's not 0. And then it reads it. Okay? One of the things, and I talked about speed, when you're working with these embedded devices in real time, speed becomes really important. You want it to go really, really, again, think of these driverless cars. I wrote a letter to the editor once pointing out that as I drive up and down 101, I see a lot of driverless cars there. At least they're not driving. Anyway, here's what the compiler generated. So it has all of this whole set of instructions here. And that's what the compiler generated for me. Here's what I wrote. This does exactly the same thing in about, I put it over here for reference, in about half as many instructions. And so it goes a lot faster. And again, if you're trying to control, think about engine control in a car too, adjusting the spark and all of that kind of stuff. Every instruction that you can save is worth it when you're doing that stuff. Okay. I know that assembly language is not as easy to read, but if you choose your comments carefully, I'm biased. I love assembly language, but I don't think it's impossible to read that compared to this. Okay? I actually find the assembly language easier to read. Okay, next reason for studying machines at the assembly language level is data storage formats. I alluded to this a little earlier. And probably you can all tell me what the value of C is in this. Anybody hazard a guess?
250.
Yeah.
0.
0. This is an integer operation that happens first, and if you divide 1 by 2, what's the integer part of it? 0. Okay? And yours is a common mistake. Well, one of the things I have to admit here, this is in C. C is a fairly low level, let's call it a medium level language. And indeed, if you're writing in almost any modern higher level language now, it'll do all the proper conversions, and you probably end up with a floating point value here. Okay. Another thing to know is that integers, of course, have a finite length. And what's the value of C here? Well, it depends. It depends. Is my integer a 32-bit value or a 60 or 33 or more bits? Is it a signed integer? That has a lot to do with how I finally display this value. Okay? If it's a signed value, it's going to turn out to be -1. Okay, so it really depends. And so you have to, if you're, again, one of my main interest is in the embedded systems, and when you're working at that level, you have to understand what's going on with these values. Another mistake that people make is that they think of floating point numbers as real numbers. And are there any mathematicians here? I know there's one. Floating point numbers are finite. Real numbers include irrational values, and it's a continuum. Floating point are not. There's a finite number. So let me talk about floating point numbers. And I'll do it within the context of decimal, because I think it's a little easier to see here. And the way they're stored in the computer is a normalized scientific notation. By normalized, what I mean is the decimal point is adjusted so that there's 1 digit to the left of the decimal point. And then it's, since we're in decimal here, 10 to some times 10 to some exponent. So let's assume 5 digits for this. And so that value, 3.65 times, or 365, would be stored as the 5 digits 365 and 02. Okay? By the way, I haven't allowed for sign here. I'm working only with unsigned values. As an aside here, I talked earlier about using slide rules. Slide rules have accuracy or resolution to about 3 significant digits. This was one of the other problems we had when we were designing the circuits for the Gemini capsule. So let's take another number. 761 would be stored as the 5 digits 761 and 02. Now, in order to do the arithmetic, you have to the algorithm has to unravel all of this and do it, carry it out more. And so this turns out to be 1.126. But that, since we only have 5 digits available, only 3 for the mantissa, we have to round it. Okay? So it gets stored as 113 and 03. So we come to the conclusion that 365 plus 761 is 1,130. Now, okay, so this is less than 0.5% off, not a big deal. I do say here, though, whenever you can, use integers. And you have access to 64-bit integers nowadays. That'll even deal with the national debt. But the problem here is that these errors, not only, it's small, but they are errors, but they tend to accumulate. That's the problem. This can have disastrous results. In the Gulf War in 1991, one of our many, many previous wars, we have lots of wars, there was this announcement that came from this site here that turns out that a Scud missile got past the Patriot defenses, killing 28 people. So how did that happen? By this time, of course, we were using computers to control these things. I've talked about, again, real-time systems. So let's look at the Patriot versus the Scud. What they had in there was a clock that ticked every 1/10 of a second. And they stored it as a 24-bit integer. And as you probably know, there's no way to, there's an inaccuracy when storing 1/10 in binary. You can't, it's a repeating number. 0011, 0011. It's like, 1/3 in decimal. Now, what they did was they stored the clock time. They multiplied 1/10 by the clock time. There was a clock that had been running for a long time. They're sitting there ready to shoot down this missile. And they multiply it by 1/10 and store it in 48 bits. Now, we've already said there's an inaccuracy in the 1/10 stored in binary. Then that's converted to a 48-bit float, and I've already pointed out to you that floats have gaps in them. They're not continuous. So the error it turned out that in this case, the clock had been running for in the order of 100 hours, and the error was very small, 2 to the -20th, but when you multiply it by 100 hours, you get about 1/3 of a second. And a Scud will travel more than 0.5 kilometer in that distance. Okay, so this little misunderstanding in the way numbers are stored in a computer caused 28 people their lives. Okay, so what you do, depending on where you work and what you're working on, can be extremely important. So I say that good programmers understand the machine that they're programming at the machine level. They write short, simple code statements. And I showed you earlier that that trying to make it look more succinct in a higher level language doesn't always buy you anything. They make it easy to change their code. When you're working in a place, you should understand what's going on in that environment. One of my jobs was working for a shipping company, and I chose variable names like port and starboard and stuff like that. I'm working in their environment. I want to use their language. When writing your comments, explain why you have done something. Some of you probably already had the experience of coming back to code that you wrote even 2 or 3 weeks ago and thinking, what was I thinking when I wrote that? So it's not just for the people who follow you, it's for yourself. Write down what you're thinking at that time, and it'll help you when you have to change that. So, I get to finish a little early here. The answer to my question, why assembly language, and the main answer here is so you understand what you're doing, because the bottom line is you're controlling hardware with your code. I think it's fun, and I talked about some of the things I worked on. Some of the things you get to work on are these. And a lot of these look really, really fun to me. And who knows what's coming in the future. Oops, let me go back. So there's plenty of time for questions, comments. I can talk more about some of the other projects I worked on. Anything?
Let's begin with a very important question. Is it easier or more difficult to write Hello World in assembly language?
Well, it's considerably more difficult. I can bring up a Python interpreter and just write "Hello World" and it'll echo what I said. So yeah, it is more difficult. There's a question back here.
For this gut thing, how does something like that pass through like the QA process? Because isn't there more than one person responsible for testing the code?
How did Volkswagen do what they did with the diesel? Somebody actually, I think what typically happens is, a better answer to your question, what typically happens is management is putting pressure on everybody to get things done right now, as soon as possible, and they don't give you the time to do things. And when you say, I'm not quite ready yet, they say, well, tomorrow is the burn date. And so they typically don't give you enough time. And kind of a corollary to that is it's changing for you guys. When I was doing this stuff, the managers were clueless about software. They didn't understand what it takes to test something thoroughly. So that's how the stuff gets through. It's kind of, you remind me though of this has been going on forever. I talked about the Horizon scanner we built. And when we shipped that off to McDonnell, they were very happy because we were the only ones who shipped it on time, and they turned it on and they were watching it do its thing. And one of their techs, while it was running, he wanted to look inside, and he started unscrewing the top, and a nut fell inside and shorted out the power supply, which I designed, and instantly turned this, essentially in today's dollars, probably $1 million box into paperweight. Okay, our tech was there. He'd gone with the thing. He was pissed, big time, because we'd pulled all-nighters to put that thing together. So this stuff happens, but you make a really good point. If any of you some of you probably will rise up into these positions where you're working for QC and stuff like that. And my brother-in-law is a QC guy for down in Silicon Valley. And he's constantly fighting with management. We need more time to show that it's right. And working on Gemini, on the space program, as a friend of mine used to say, brain surgeons don't say oops. You're dealing with lives there, big time. Tia. Yeah.
So can I add something to your previous slide?
Yeah.
Good programmers.
Oh.
As the current instructor for 460, I would also add that good programmers understand the language that they're working with.
Right.
Know that when you do things like divide two integers, you're going to get an integer, and that's going to vary from language to language. So understand your language.
Yes. More questions?
I'm not really sure if it is related. You're talking about speed, and you know, like how new engineers or programmers are designing like just machines that are used in factories, and they're like just high on speed, and I mean everything doesn't really require a lot of like people to use these machines, but also these machines are getting people hurt, you know, because of the speed. So I'm just kind of wondering if it somehow, you know, like some of these programmers get to be in contact with like humans and not just with computers, and actually just kind of like see that humans will be using these machines and not just actually a robot or something like that. So what can you just say on a speed and like when you're creating a machine that actually a human is going to use, you know, like, I don't know, like, I can say Medtronic. I worked at
Right.
Medtronic, and they, their machines, they never stop. They have to be running 24 hours, and we have to produce millions and millions of cutters. So I'm just wondering, and when people do get hurt, they just get pulled aside, kind of just, they're worthless. So what do you have to say, like, to new engineers coming up, like, when they create machines like that, like, in terms of thinking of people, like,
Yeah,
it's speed.
you bring up a really, really important issue, and I feel it all the time as I'm looking at the development of driverless cars, and you know the algorithms are logical, and humans are not. We are not logical beings. We're good at we're irrational. We're good at rationalizing our behavior, but we are irrational. And I remember several years ago driving down 101 in Santa Rosa, you know, on the freeway, and I'm going 65, 70 miles an hour. I'm not an especially slow driver. And out of the clear blue, this car, you know, he was going at least probably 100 miles an hour, came up behind me and cut around me so close. Okay, I have a Prius, it's light, but the car shook. He was so close. What are the algorithms going to do with that? This is the kind of thing I think you're talking about, and I don't know how to deal with it. I think that you need to be willing to separate yourself out and think about the humans. I've mentioned the Volkswagen diesel thing a couple of times. You know what bothers me the most are the engineers that did that. I was a software engineer for a long time, and I can tell you if a manager told me to do that, he'd get a one-finger response. You know, I would not do that shit, excuse me, but I mean, that's awful that a software person actually sat down and designed that. Think of the humans involved. It's really, really important. I actually had, and I'm not just saying this either. When I was in junior college, I went to junior college in Southern California, Pierce Junior College, and you who might be from the Valley, and I had a job working as an engineer's aide for Marquardt. Marquardt built the ramjet engine for the Bomarc missile, and they tested them there. And my job was take the test data and plot it to see if the fuel system behavior fell within the limits. And one time we got a system that was just slightly outside the line. The engineer who designed that was really pissed off at me because I wouldn't sign off on it. I said, if you want to sign it, go ahead, but I'm not going to. So, you know, pay attention to this stuff. This goes back to the QC question back here, too. Don't let them push you around, really. You know, stand up for what you know is right and think about the humans involved. I think it's really important. Question here.
Have you ever had management ask you to do something unethical like that?
No, I haven't. Well, except that one time that I just mentioned. He wanted me to. In fact, the engineer who did it got me the job in the first place. He was the father of one of my close friends, and I was looking for a job, and so he actually got me the job. And he wasn't very friendly with me for a while, but I'm just not going to do that. I mean, it's just unfair to those people around us.
May I ask you a question about assembly language?
Sure.
How about different assemblers that you have encountered in your career? Are there some assemblers that stand out in terms of readability or help to the programmer and the number of opcodes, that sort of thing?
Not really. I've worked with at least a dozen different assemblers and probably that many different architectures. And one of the most I mentioned working at a shipping company once, and I was a contract programmer before I came up here back in the early '80s, and I had two major clients, and one of them used an IBM Series 1 mini computer, and the other used an Intel chip, and the order of the operands, source, destination, were opposite. And so I'd have to go source, destination in the morning and destination source in the afternoon. And, you know, you adjust. I want to give you another hint. I've run across an awful lot of programmers in my life who say, well, I'm an ex-programmer. You know, this is what I do. Look for opportunities to learn new things. If they want to ask you to do, use a different assembler, a different compiler or something like that, that's an opportunity for you to expand your resume for your next job.
That's good advice.